we going to start? Okay, so first lecture by Herbert. I did the same on integrable many-body systems and GHD. I don't know what GHD is.
So GHD is generalized hydrodynamics. I thank you. Well, it's too long to buy that. So, anyways, thank you very much for this invitation, and it's a real pleasure to see many people working in these topics. And well, I put here integrable many-body systems. Generalized hydrodynamics. I mean, this could be a semester course, so to speak. I mean, we had already 2 or 3 talks maybe in this program, but well, there will be not too much overlap. I mean, so I will start fairly elementary and sort of will put my own emphasis. So don't worry in terms of overlap. So of course, I mean, this is a huge area. And another title would have been integrable many-particle systems with random initial data. I mean, this is really sort of the more accurate title because, of course, I mean, this problem, from the physics side has been always sort of present somehow. People, it was clear that once you had integrable many-body systems, I mean, you would try to understand something about the thermodynamics of the system, possibly maybe also about the dynamics. But this was never sort of a really very active area. I mean, go to the list. I mean, it goes. I mean, these integrable systems go back to the 60s, and of course, in the meantime, people have worked on this, but was never, was never sort of the main focus. But then, was sort of somehow, I guess, sort of the push by the quantum community, which sort of wanted to know more about these systems, and there's an important date here, which I will come back to. So there's a breakthrough paper from 2016. I will tell the authors and all these things a little bit later, where, for the first time, I mean, people understood how to write down the hydrodynamic equations for these many-body systems. And that was sort of very important because, it was sort of a new tool. And then since then, I mean, you have every day you open the computer, I mean, there are more papers on this, okay? So, of course, for what I do, I sort of have to do a selection. And but before doing this, I want to advertise that actually I wrote a book on this topic. I mean, so here you can see the book. Okay, now you wonder what is sort of sitting here on the book. I mean, these are actually so the time is this direction, space is this direction, and you have particles which are governed by the Kalocza-Moser model. I mean, these are classical particles in one dimension with an interaction potential which goes like 1 over sinh squared. So it's a repulsive potential, and this is what they look like. Okay. It's nice to look, but you cannot do anything with this picture, right? I mean, so this will come. Okay, so let's see. So I want to actually really start something which sort of course, some people will know, but others will not. I mean, so I first want to start with the conventional hydrodynamics in the context of these one-dimensional systems. Okay, so maybe I should emphasize, integrable automatically means that you're sort of in one space dimension, and higher dimension, of course, there are results, but they are much more sparse. Okay, so and let me do it just a simple chain, because this will come up over here, and so we take a Hamiltonian maybe with the sum over the kinetic energies, and then you put. Let me call it sort of an index chain here. So that's the chain potential. And this depends on the difference. Okay. And this difference, this is also free volume. I mean, so I will call this arbitrary. So you can think either of a equally spaced lattice. And, at each lattice size, you have sort of degrees of freedom, which are the free volume and then the momenta, so that's one way. But of course, you can also think of, so this would be C.
Sorry, Herbert, may I ask you to press a bit more, because it's very difficult to read. It's very difficult to read what you are writing.
Yeah,
it's
well, because there's no light. I mean,
but there is no way to put light.
There's no light. Yeah. Well, I put an, yeah, I mean, Yeah, no, that's, I cannot write, you know,
No, there is that.
there's light, I mean, this,
We got this.
they used to, they,
Suspect it's the glare.
no, but that's even worse, I mean, no.
Can you speak from there? I can just move.
Maybe there's,
No, it's hard to see also.
but
It's a strange because it's not very simple.
it was never like this, I mean, sort of,
I will move it wrong, so.
no, I don't know,
No, but it's little.
or maybe,
Okay, yeah, is better.
or maybe, well, okay.
You can only make it work. Yeah.
But we didn't have this problem before, right? I mean, anyway, so anybody has to move in front, okay. Oh, but I don't know why these are,
Yeah, usually it's stronger.
they should be,
Push it or something.
um, well, okay, so yeah, but that's a pity, right? I mean, I cannot. There are physical limitations in order to make it even brighter. Okay, anyway, so all right, okay, yeah. Maybe for maybe but for the next time, maybe we could really find. I don't know. It's really strange because but there's nothing really here. Laptop volume. It's just the volume which is controlled. Anyway, so maybe you can find out. I mean, what's actually happening. Anyway, so what I wanted to say is that okay, so the other way, of course, is that you can think of the real line. I mean, so you have position and momenta, and so maybe you have something like QJ here, and maybe the QJ here. Of course, I mean, these QJs, they can overlap, and so the free volume would be negative in this particular way, right? And so here you have the particles sitting. All right, so then the first thing is when you do thermodynamics, so you want to look at the conserved fields, and of course it's easy to find them. I mean, so you take first what I call Q0. I mean that's the summation J over RJ. So this is the free volume or the inverse density, whichever you want to call it. I mean, and it's conserved because when you take the derivative, you see that. This is the difference of momenta, and so it has, it has this conservation type form. I mean, the time derivative of that quantity is a discrete conservation law. And then the next one would be I put the sum over the momenta, and then of course there's also the energy, which is the summation over EJ, and the EJ, of course, is the quantity sitting here, right? I mean, this is equal to EJ. Okay, so we have a vector of C conserved quantities, and one question you might ask: are there more? Okay, and that's actually an interesting question. There's beautiful work by Shiraichi, which at that stage I want to advertise here. Maybe some of you in the audience might know, but anyway, I mean, so you could ask the same question in the context of quantum spin chains. And what he proves is that for quantum, so it's spin 1/2, spin 1/2. And I guess at the moment, I mean, it's still, there are various papers. I guess the most recent papers are this interaction which are next nearest neighbors. And in this case, there is a dichotomy. So you have either the trivial conserved quantities. So trivial means that, which you can guess, or there's some symmetry. Of course, the Hamiltonian is conserved, but maybe spin is conserved and things like that. Okay. Or you have infinitely many. There's nothing in between. And that's really, you see something happens.
What's that thing? Can
Okay.
Now life is much better. Okay, now I'm really seeing the last point.
Okay. All right. Okay. Okay, so it's 1/2. I mean, it's trivial or it's infinity. Of course, this is something which has been guessed, and then but I mean, this is the first really complete proof, and it's very nice because it really tells you that. When you look at these conserved quantities, later on we are going to write equations for the conserved quantities, and you better don't miss one of them. It has a slight disadvantage because there's a lot of discussion of conserved quantities which are not strictly local. You see here, in this case, actually, the conserved quantities are only one body, right? I mean, it's just sort of depending on. I mean, this one is a one body in terms of the R variables, and all of them are one body. But and they're strictly local. But in general, I mean, you might think that you might have densities which have sort of like an exponential decay, and this, in some sense, would have to be included. But it will be not of any importance in our context. I just wanted to communicate that when I saw this result, I thought, well, I mean, then why don't I take this system and prove a similar thing, right? So you start. I mean, then you take first one body observables and try to see whether can write. You look at the time derivative and you try to look whether it can be written in terms of a difference. Now, if I do one body, I mean that's still a computation which you can do. And now you take one and two body, and I really worked for quite a bit. I mean, because I thought it must be doable. I just couldn't see how it works. Right? I mean, maybe it's not true, or anyway. I just want to say that I think it's a very, very nice advance, but it's somewhat special for sort of special. I mean, I mean, of course, it uses the fact that somehow these spin 1/2 objects seem to be simpler to be handled for that particular question than discontinuous variables. Okay, so now we want to do hydrodynamics, and then okay, so the next thing what we want to do is we want to do the Gibbs. And the rule of the Gibbs, of course, is that's 1/c exponential, and then I have to do the sum of the exponential is a linear sum of the conserved quantities. So this is here the pressure, or at least sort of proportional to the pressure. And but you see the point is that we have to take all of them. I mean, so there's some the dual variable to the momentum. So I take Q1. And then there's sort of the Q2, and you see that here for this lattice history it's particularly simple because it's all one body, and so that's just a product, right? I mean, so in this case it's very easy, but later on, I mean, we will look at integrable system, and then you have many more conserved quantities, and then there's sort of an issue of how to actually write down this kind of Gibbs measures. Okay, so now the next step, what we want to do is you want to look at the currents, and let's see. I guess I think I put them. I just want to make sure you see the same notation. Yeah. No. Okay. So maybe I should have sort of be a little bit more formal. I mean, so this is of course relative to the volume measure, right? Okay, so now I can look at the current, and I look directly at the current densities, and it's just a simple computation. Here it's minus Bj, and then you have the force, which is V prime of Rj, and then you have difference in momentum times the force. All right, and now, if you want to do hydrodynamics, I mean, you want to actually compute, what are these currents? And so here I put, let's say, maybe an index alpha up here, and I have to do an average with respect to this particular Gibbs state. So there will be the P, there's the U bar, and there's the beta, right? And now, of course, everything is very explicit, and I'm not going to write the formulas. I mean, this is sort of totally unimportant for my purpose, but you see that there's enough convexity around so that I can sort of, use these variables, and I can sort of express this in terms of the average densities. So I have not introduced the average density, so let me do this down here. So the average density, Q alpha, let's say at the origin with respect to this E mu bar beta will be equal rho alpha. And then, this will be a function, that's the point alpha. This will be a function of rho. Okay. And now comes sort of, this hand waving business, and we want to do generalized you want to do conventional hydrodynamics. So, you're thinking of states which sort of locally will look like the Gibbs state. I mean, so basically the way you should think about it is that, rather than taking here let's say, the total conserved quantity, I mean, you sort of, put some slow variation inside the sum over here. And then, you argue that the system sort of maintains local equilibrium, and therefore you can sort of write down a closed equation for the evolution of the conserved fields in case that the initial data are slowly varying. And so the net result of this is that this is just sort of thermodynamics. Now, once you have slow variation, then these objects become functions of space and time. I mean, so you have here, this is the usual hand waving, but I just want to do it briefly. I mean, so here you have time and space, and then so in a little volume, you're thinking that it should be, this is sort of the xt, and in this little volume, you will have this Gibbs measure, and therefore, it can be identified with having these particular densities. Okay, and then the macroscopic conservation law is simply that have to have the rho alphas, and so that these are functions of x and t, and then you have plus cx, and then you have the currents g alpha, and that's of course a function of rho vector x of t. Okay, now it's equal to 0. Now, this is hand waving, and it will stay hand waving presumably for a long future, because this, while it looks very natural to actually provide a proof, is sort of pretty much out of scope, at least sort of. I certainly in this context, and anyway, I mean, I just want to say that this is a difficult problem. But numerically it works very well. I mean, so sort of typically what you do numerically, I mean, you run lots of simulations on these kind of systems, and the two best choices, where these things sort of work very well is I mean, you do a potential which sort of like what we call the shoulder potential, which looks like this. I mean, so this is x, and here you have the chain potential. I mean, this is one option. And I mean, it's actually fascinating to see this. You see, I mean, these hydrodynamic equations, I mean, can have shocks. I mean, so, you have smooth profiles, and they can suddenly sort of develop sort of discontinuities. And it's really amazing to see, I mean, these particles, I mean, whatever they do, I mean, they just have to follow these differential equations, and then suddenly, they try to form this shock. And I mean, I still find it sort of fascinating, how there's no force guiding them. Well, I mean, it's a hydrodynamic equation which they have to satisfy. Okay, this is one choice, and the other choice, which it looks even simpler, but which numerically is very efficient, is that the other choice which you do is you take alternating, not random, just alternating masses. So I mean, this you forget. I mean, you just sort of do the usual pair collision sort of, at the point, but you imagine that you have alternating masses. Then the unit cell is sort of 2, and if you take the golden mean of these two masses, I mean, then this kind of approach to equilibrium sort of numerically works extremely well. Okay, so this being said, I sort of want to explain you a little bit what I'm planning to do in this talk. So this is sort of some sort of outline. Okay, and I want to sort of generalize, this conventional hydrodynamics to the case where we have many conserved fields, and to do this, it's sort of good to look at the specific case, and the case which is sort of currently, in some sense, best understood. Let's see on the classical level. I'm not talking, or maybe I'll only make some vague remarks on quantum systems, but it's one of the best understood systems, and so I want to look at the total lattice. And I will just go through this program here step by step. So I will do the generalized Gibbs ensembles, and so this is a generalization of this formula here. But, writing down the formula, I mean, this you have seen many times. I mean, that of course doesn't help, but in this particular case, I mean, you write down the formula and you can do actually sort of a fairly deep analysis. And I want to give you some of the indications over there. There's something which is called TBA, which sort of results from the fact that, well, you will see it's somewhat surprisingly that the free energy can be written in terms of a variational problem, and then the TBA is sort of the Euler-Lagrange equation for that variational problem. Okay, but then the key point is that this 2016 revolution. The key point is that if you want to write down, even just write down your hydrodynamic equation, you better solve this problem. I mean, you have to compute the average carbons in terms of a generalized Gibbs measure. And, this is sort of a little bit less obvious. Okay, so then I want to talk about the average carbons. And I think that's sort of essentially, maybe I want to talk about large deviations. Anyway, I mean, this will be short sort of remarks more or less, but maybe I should put this also here. Okay, so this is the total lattice. And then the second point which I want to do is, I want to look at something which is called the Ablovitz-Sladek model. So the Ablovitz-Sladek model is a discrete integrable version of the nonlinear Schrödinger equation. And I mean, that's in the defocusing case. And there are two things which I wanted to show you. One of them is that, I mean, each one of these systems, I mean, each one of these integrable systems, they have totally different definitions and then, also tools in order to analyze them. But once you come to this hydrodynamic scale, somehow, there seems to be a common structure. And I just want to, I mean, this is sort of a general sort of agreement. And whenever you find new models, I mean, it seems to be sort of really following that schema. But sort of just to emphasize this a little bit more explicitly, it's sort of useful to sort of take another model where you can see while things are different on the large scale, they become the same. And in particular, I want to do something which I did with Alberto Brolo. I mean, I want to tell you how to do the scattering theory, which at first sight sort of look like a very trivial problem, but in fact, I mean, one can say much more than we initially suspected. And then we'll be sort of, well, since I have 3 hours, I mean, I want to spend sort of the rest of what is left over is sort of, when you look at these things, there's one sort of, obviously missing. You see, we're looking at integrable systems. So you open the book about integrable systems. I mean, it could be Toda, I mean, could be Ablovitz-Sladek. Look at the books of Ablovitz, for instance, or any one of these books. And the first thing what they do is they do inverse scattering methods, right? And this is totally missing. All what I'm doing here will never use that tool. And so the question is, what about, okay, so here I want to talk about solitons. I mean, sort of the way how it's usually understood in the literature, inverse scattering. I guess they use both an inverse scattering method or inverse scattering theory is also another one which. Now this is sort of much more tentative, and I don't have to say sort of new things, but I just want to emphasize that there is somewhat this tension that we are doing these things without actually using, what people consider to be the most powerful method in this area. All right, so let's see whether I have to say something else. No, I think that's fine. All right, so let's do a little bit of TODA. Okay, so I guess so I just keep going here. Well, this was conventional hydrodynamics. Okay, so the TODA will have sort of several chapters. I mean, so the TODA lattice, TODA. Okay, and the TODA lattice is sort of a very special interaction potential. I mean, so this of x is just the exponential potential, right? I mean, so I still have the same Hamiltonian. All the symbols stay the same. I mean, I have position momenta. I mean, I have the free volume. But now I look at this very special case, and you know, as far as we know that if I take, you know, if I take this this chain potential is a smooth function, then that seems to be the only choice I can do. Okay, and so I just go through the list which I put up here. So let's see. Okay, so we have to first do the conserved currents, and well, the conserved fields, currents, and then the GHD. Okay, so conserved fields. Okay. All right, and so for this we use the Flaschka variables. So this is a famous paper of Flaschka. I mean, you see, I mean, it's named after TODA, and of course TODA already figured out that, you know, and a lot of evidence that then you know, that the system would be integrable. But then Flaschka sort of introduced the correct variables. I mean, he was at the Courant Institute, and so, you know, he knew that you had to find some sort of Lax matrix in order to do this. And this is, you know, what is the basic tool in all this area. Okay, so the Flaschka variables are HA, and you take just e to the minus the RJ over 2. Okay. All right, and now you can sort of, well, there was sort of an interlude. I mean, Henault sort of, you know, amazingly guessed already what the conserved quantity should be. But you know, the really, you know, from a technical point of view, having the Lax matrix sort of opened up the door. Okay, so now you can write down these equations of motion in terms of these new variables, which I will do. So the HA, and that's the 1/2 of let's see. Now the equations of motion actually become, you know, simply with quadratic nonlinearities, and okay, and so the way you should look at it is that now you know, if you see your lattice, I mean, so you have my lattice variable. So now at each side I have the HA and the RHA, right? And you see that this gives you a coupling through the PJ to the right neighbor, and this gives you a coupling to the left neighbor. These are two variables, I mean, which are not symmetric, right? I mean, well, it's just like originally. I mean, you know, I mean, the stretch and the momenta are not you cannot interchange them. There are other models where you have more symmetric structure, but this is sort of what you have here. Okay, and now the nice observation is that you can introduce the Lax matrix. So, you know, this comes from work on the KdV equation. I mean, you know, there was a whole industry at the Courant Institute, and then further on, I mean, we sort of realized that having such kind of an object is very useful. I mean, so in our case, so I call it n. I mean, you know, I should be pedantic and put the index n over here. It's an n by n matrix, but you know, eventually n will go to infinity. And I think, you know, it classes the notation a little bit, and it's not really necessary. I will emphasize, you know, if it's really very important. anyway, so what you do on the diagonal is you put here the Pj all the way to Pn, and then here you do the A1 up to An minus 1, and here you do the A's also. So it's a symmetric matrix. It's a Jacobi matrix, and then you know there's sort of this point here at the end. I mean this one and this one. And there you have two choices. I mean, so if you want to do the open chain, I mean, so the open chain basically means that you know, when you look at this and I take n particles, I mean, then you have to sort of ask yourself, you know, what do I do with take n plus one, and then the open chain is just you have n particles and you let them sort of escape to infinity. I mean, so they're not confined by any volume. This would be the open chain. And for the open chain, I mean, you put this quantity is equal to 0. Okay, so this okay, and then you can do the closed chain. So the closed chain is sort of the obvious thing what you would think, right? I mean, you just sort of you just identify up to slope. I mean, anyway, so it's an obvious periodicity condition. And the closed chain, I mean, you put this equal to what is called An. I mean, so this is An minus 1, and here is the An, and here's also the An. And then there is a companion matrix, which is called the B matrix, which is 1/2, and you know it looks the same. I mean, so on the diagonal you put 0. On this side, I mean, you put minus A, and you put A here, and here it's minus An, and here it's plus An and minus An. And the rest, everything is also 0. Again, it's a tridiagonal matrix, so it's a Jacobi matrix, and you have these boundary conditions over here. And then you find this amazing identity that if you take this matrix and you insert the time evolution, and that's the one which comes from over here. So let me just say that this depends on time, and then you can write this as a commutator, which is B of t of t. And from this, of course, I mean, you can learn many things, and therefore, it's just having the Lax matrix is sort of like an amazing tool. And so let's see what we can learn from this. I mean, so first of all, this Lax matrix. I mean, now I put here maybe the n. I mean, just to make sure. I mean, of course, it has eigenvalues which are lambda j. So HJ, right? And so eigenvalues go from, of course, they're real because it's a symmetric matrix. And now the point is that, when you look at this commutator, you see that the eigenvalues are actually conserved. So whatever, the ddt of the lambda j under the total evolution is equal to 0. Okay, so fine and great, and we have found n conserved quantities. I mean, that's great, but now you look at these eigenvalues, and then you realize that the eigenvalues are non-local. If I take one of these eigenvalues and if I change somewhere, the entries of my matrix, I mean, then this eigenvalue will float around. I mean, there's no chance to, if I change here, the whole spectrum will be somehow modified, and I cannot guarantee anything. And that's of course from a physical point of view a disaster, because I didn't emphasize this because it's so useful, but so used. But of course, it's very important that. I should have not only a globally conserved quantity, but it should have a density which is local. Otherwise, you cannot do hydrodynamics. And so there's fortunately a simple way how to resolve this issue. So the way you define the globally, I mean, the globally conserved quantities which have a density, you just take the trace, and then you take the nth power of this matrix. I mean, this, it's always for fixed capital n here if you want to read these formulas. Otherwise, I mean, this object would not be traceless, and it doesn't make any sense. Okay, and so of course you can use the spectral theorem, and then you find that this is simply the lambda j to the power n. And now, of course, it's also the same as when I work out the trace. It's L to the n over the diagonal element. And so you see that obviously, you know, when I looked at of the matrix elements of the nth power, this is now the density, right? Okay. Now, now here I cannot take any infinite volume limit, but you know, but once I have this formula, of course, the density you will have an infinite volume limit. And how can you see this? Well, I mean, that's not hard. So what you can do is you can just you know, you realize, you know, it's a triangle matrix. So you know, if I take the nth power of this, I mean, you know, it will be, you know, will be still sort of supported on a strip of size of diameter n. I mean, will be a matrix which looks a little bit wider, right? I mean, like this. But then when you look at this matrix elements, clearly it's a sum over strictly local quantities, right? I mean, so. Okay, so now we have found actually the local densities. So let me just sort of put this as a conclusion here. So the Qn of K. Okay. All right, so that's fine. And well, so you look at the formula, and then you see that the Q1 is just the momentum, just like before. I mean, the Q1 is the summation over the Pj, so that's the momentum. The Q2 is twice the energy. So that's just like in the case which I just erased. But now you might wonder, what about a Q0? Well, that's sort of not really given by the Lax matrix. I mean, so, you know, on top of the conserved quantities which you get from the Lax matrix, you have to add also the stretch. So Q0 J will be Rj, that's the density, will be Rj. And this is something which sort of, I mean, free volume or stretch, I mean, that's a term which we use just to make sure that sort of, you know, if you think about particles, it's the inverse of the density, and it's clear physically that that's a very important conserved quantity, and we better don't really, we better keep it. Otherwise, we cannot do any hydrodynamics. Okay, that's fine. Okay, so well, I mean, if it's Rj, but of course the Rj is nothing else but the log of Hj squared, right? So this is the quantity which we're using here.
This is n going to zero limit.
N going to zero limit. Why do you want to? Oh, you mean, well, yeah, yeah. Or you think that you know, it should be somehow hidden in n equals zero limit of, yeah, maybe I could write it also. But since there's such an explicit expression, no, that's fine. Yeah, you can certainly do that. Okay, so and then you know, of course, I mean, this I will come to this because it will be in fact a very important identity later on. I mean, but at the moment, I'm you know, it's sort of not very transparent. I mean, you see that this is of this form, and okay, I'll come later on back to this, but. Okay, so maybe I should say one word. I mean, why do I emphasize this here at that stage? Is that you see that when I look at the current, it's itself conserved, right? I mean, you see this is the stretch, and the current is the momentum, and the momentum is itself conserved. So that will play an important role later on. Okay, so the next point I want to talk about the integrability. Well, I have already the integrability, of course. And let's see what. Okay. Integrability. It's just sort of it's a more general thing about, you know, way how you would try to do this kind of things, and for this, you know, of course, I mean, there is this. this notion of having n conserved quantities. I mean, that's certainly one important input. But now you could sort of you could ask yourself, whether it's sort of integrable in the sense of classical integrals, classical systems to be integrable. And I just want to mention this as names. I mean, there's someone, mathematician from Zurich. I mean, Kappeler. I mean, he did the closed case. So if it's closed, I mean, then you have you have the sort of that the phase space is foliated into tori, and this n tori, and then you have sort of quasar motion on the n tori, and this is sort of a complete mathematical sort of treatment of that particular case, right? I mean, and the words are okay, but you have to also do a little bit in order to get this, right? So you can then sort of do action angle variables, and then anyway, so this is done in this work. I mean, I guess it's I mean, just that you have sort of an idea of the time scales on which these things are working. I mean, this is 2008. And then there's a famous work of Moser. I mean, that's the one from the Kamm theorem. Of course, he understood these kind of things already very early on. I mean, this is 1975, but he looks at the scattering theory. So, which it's a priori sort of not really so closely connected, right? So what does scattering theory mean in this case here? Where is the evasor? The evasor has disappeared. Here. Okay, so let's do the scattering theory here. Okay, so the scattering theory is something which people sort of for a long time. And so here you take X, and here you take D. Here, now I'm thinking in terms of particles. And okay, so you maybe have few incoming particles like this, and then here you have a world which sort of strong interaction, and you don't really know what's actually going on, right? And but then if the system is integrable, then actually the assertion is that when I look then at the large future, you will find a velocity in the outgoing case. And so, if I put here something like this, maybe it's shifted by something over here. Maybe I could put some color. So this is the actual trajectory. Okay. And similar for the other ones. If I put like this, and then, again, it might be shifted to the other one, and for this one similarly. Okay. And for the total lattice, I mean, this picture was proved by Moser, and one can also derive a formula, which I'm going to write down in a second. Well, I mean, Amol explained this to us some weeks ago, but maybe others have not heard this. You can sort of compute what is the relative shift, actually. I mean, this will come in a second. But I just want to point out that this is actually a general result. I mean, there's work by Andrea Hubacher. Actually, it was a master thesis, which sort of a little bit surprising. I mean, sort of because it's a brilliant piece of mathematics. But Andrea Hubacher, I don't know what happened to her, but she looked at the general repulsive potential. And then you look at the momenta, and of course there will be asymptotic momenta. Let's say plus minus times t. So t goes to infinity, and there will be a shift which I call phi j plus minus. Okay. And this is a completely general result, and then you might say, okay, at infinity, I mean, particles have their velocity, and therefore, these velocities are sort of conserved quantities. But that's sort of a little bit too fast. I mean, when you look at the map of sort of, here, the incoming map to the outgoing map, presumably it's a very chaotic and singular map. I mean, so whether you can deduce anything from that, it's not so completely clear. But the miracle is that in the case of the integrable case, so in the case of the total, you do find that this asymptotic velocities, if I take the incoming velocities, so at minus infinity they're far apart, and therefore the Lex matrix is diagonal, and therefore these eigenvalues sort of are the same as the incoming momenta. So this is the lambda J. And then when I look at the outgoing momenta, I mean this is just this picture up here. Then it's lambda n minus J plus 1. That's only for the integrable case. I mean that you have sort of this high regularity structure that when you look long enough, when you look at late times or at early times, and when these have separated, I mean then you know what the velocities actually are, and you can also compute the shift. So these things are used experimentally. I mean, sort of time of flight method, which uses this. You see, basically what you do is, you have your system, and then you want to determine, what kind of what kind of asymptotic velocities do I see? And then you have to isolate your system. You have to let it run. I mean, you have to sort of really do the scattering experiment, and then of course you can see this directly. Okay. Now, in our case, I mean, we are in a much better situation. Namely, so for the total, we have, so for instance, if people, I mean, let's say for the delta Boser gas, I mean, this time of flight method sort of is the one which is typically used because otherwise it would be difficult to actually see what the quasar particle contact is. Maybe I should mention one word, which will come over and over again. So now we have the quasar particles. So the quasar particles, I mean, so this would be number one, and then as I follow, it's sort of like a free particle, but then it does a little shift. So this would be one, and it would be two, 3, etc. Right? I mean, these are the quasar particles. And what I wanted to indicate is that, once I'm in the region of strong interaction, then maybe it's not so easy to distinguish where the quasar particles are. Okay, so now in our case, I mean, since we have the Lex matrix, we have sort of something which I would like to call sort of the Lex microscope. You see, if I want to know what kind of spectral parameters I have somewhere here in the middle, with my naked eye, I cannot do it. I mean, that's sort of, and that's also, you can see from the cover of my book. I mean, if I want to know, what kind of spectral parameters I actually see, I mean, this is sort of totally impossible. But now we have the Lex microscope, which is a very simple procedure. I mean, I look at locally at some collection of particles, let's say 100 or maybe 500, and I want to know, what kind of quasar particles are actually contained in this particular volume. Well, the rule is very simple. I just form the Lex matrix of 500 particles. Here it is. The P's and the A's are supposedly, I can sort of take them, let's say, from my computer simulation, and then I find the eigenvalues, and it's the eigenvalues which are the ones which are then because these are the conserved quantities which tell me which kind of quasar particles do I see. Okay, and so later on, I mean, in the terms of the hydrodynamics, it's the density of the quasar particles, which is sort of the slowly varying quantity. You see, it's a little bit more or less intuitive because we don't have a direct physical tool to see them. Usually, I mean, energy, things like this, I mean, sort of a little bit better in terms of observable, but nevertheless, because of the Lex matrix, we have a very easy, simple procedure to find out, what is the density of quasar particles in some given volume. And those people who heard, listened to Amol's talk, I mean, he actually actually sort of goes much deeper into this idea of the Lex matrix microscope, because he's also looking at the eigenvectors. But that's his story, and so I don't want to enter into that all. So I couldn't anyhow. All right. Now let's see what is the next chapter here. Okay, so now, so it takes time, but maybe it's, okay, so next, so this was integrability. Let's see, yeah, 2.2. So now the next thing which I want to do is I want to do the generalized Gibbs. So now we so this is usually called GHD, I mean generalized Gibbs ensemble. Okay. And at the beginning I told you already how to do that. And so let me just write it down. So actually, so so I will do a sort of a canonical or claim canonical. Actually, it's a canonical prescription. So I do fixed n. And I have periodic boundary conditions. And then, well, then it's just a standard rule. I also take 1/0. So now you have to convert the volume measure into the A's. I mean, this is a simple computation. So I have to dpga, HA. Okay, so I get, well, then I get HA. Well, from the volume element, I get -1. But then I want to work grand canonical with respect to the R variable. So I do something which people call the pressure ensemble. And let's see, what am I doing here? HA. Okay, so I put for some reason there's a 2. Well, I guess the 2 comes from the definition of the, I mean, the A variable is e to the minus RJ divided by 2, and that's 2 comes in, then -1. Okay, so this is the sort of the free volume, the a priori volume measure, which has a parameter pressure, which in some sense sort of controls the density of the A's. I mean, so this is a pure product measure. Okay, yeah. And then we follow the rule. I mean, e to the minus the summation over n equal 1 up to infinity. N equal to 0 I have already. Then I put some chemical potentials. And then I put the trace of, so it's finite volume. So now I put an n here. Okay, and the mu n's, I mean, these are chemical potentials. They're supposed to be independent of this, of the size of the system. Okay, so this is the formula which we have seen already many times, and that's fine. But you see, I mean, in some sense, this is a rather clumsy notation. Of course, it's correct, but I mean, a little bit more transparent is actually to just use the fact that this, just by the function calculus of matrices, I mean, this is nothing else, the phase of V of L. And, in this particular case, I mean, the V is just given as a power series. Now, let's say V of W. It's just given as a power series of mu n W to the power n. But so this looks a little bit nicer, you see, than what I have to put here is then, if I may do this just by erasing this quantity here, that you see you have here the trace of V, and so this is the definition of my GHD. And of course, you might wonder what kind of potentials, I mean, what kind of V's can I take here? And, I like to call, it's a little bit confusing, but I didn't find sort of better words for this. I mean, so the V, I call this the confining potential. This sort of comes from random matrix theory. where people call this confining potential. Now, what is it actually confining? Well, you see, this was written in terms of the eigenvalues. So, you know, it's confining the eigenvalues. I mean, the eigenvalues of the Lex matrix in my generalized Gibbs ensemble should not be able to escape to infinity, right? I mean, it's just like, you know, the velocities. I write down my Lex value, which of course is something which is integrable, right? And the same thing sort of comes from this function. So you might wonder what kind of condition you might want to put. Well, okay, so typical sort of thing would be that, no, I want to have sort of like a lower bound, maybe what did I put here? Yeah, maybe some coefficient plus linear, right? I mean, this would be typically okay. But there's not so much understanding of you know, which class of potentials one can actually do. I don't want to enter into this; it becomes a little bit more technical. But I want to mention that there's you know, very nice work by Nina and Guyonnet. Alice and Roman. And they sort of investigate this sort of little bit more from the mathematical side. I mean, you know, for which kind of confining potentials you have infinite volume limits, there are all kinds of things. So just want to mention the reference, right? And the other thing which I want to, let's see, no, okay, so this comes a little bit later. Okay, so now you see what if you think about the kind of structure I erased already the Lex matrix over here. So you see the mathematical structure which we have found here is a random Jacobi because it's a triangle matrix. And the entries are under, you know, not just anything, but under GHD. And when you look at this formula up here, if I, okay, so maybe I should have said this, or maybe I can do it now. I mean, so when you look at this formula, then you see that there's a special case, which is the thermal equilibrium. So the thermal case is just that d of w is simply 1/2 b to w squared, and so you see that you know I have to put this function in here, so I get the pressure from here, and when you work out, you know, it's the trace of L squared. And so you see that it's quadratic both in the A variables and in the P variables. So when I look at the thermal equilibrium, you see that it actually has IID entries. I mean, so I can put it here. So along this diagonal, I mean, you have the P's. I mean, they are just Maxwellian, so they're just Gaussian. And the off diagonals are not really, I mean, it's still IID, but then they are, you know, they still have this factor here. So this is what people call, I mean, so P is Gaussian, and so this is P, this is A, and A is chi distributed. And I have two parameters, I mean, the beta and the P, and in general, you know, the quantity which labels my GHD is this confining potential V and the P. Okay, so these are the parameters. So the parameters, I mean, just make sure that we have this written. Parameters are always P, the pressure, and this confining potential.
Or which matrix are you plotting?
Mm-hmm.
Which? Oh, this is the Lex matrix that you're writing.
What was that? Okay, so here I was trying to say that okay, here I just plotted against the Lex matrix, right? I mean, so the P's are on the diagonals and the A's are the off diagonal. I mean, okay, and now if I do it thermal, then what I realize is that you know, I mean, since I have to take the trace, I will get the square of the diagonals and the square of the off diagonals. And so this factor will become a sum of squares, both for the P squared and the A squared. Then for the P's, I mean, you see there's nothing else. I mean, the PJ, I mean, the momenta, there's nothing else. I mean, that's just a usual Maxwellian. And then for the A's, of course, I still have this prefactor here. And therefore, you know, this is what people call the chi distribution. Okay, so now the next question you might ask is, I mean, that's fine, but what do we want to know about this Lax matrix, right? What do we want to know from this random matrix here? And you know, you do random matrix. Let's see. I mean, I'm almost time. Well, we have maybe you give me sort of like 10 minutes, right? I mean, then. Miss some time. Okay, so well, I mean, we have a random matrix, and the first thing what you ask is the density of states, right? I mean, that's sort of the most natural thing to do, and that the same thing what we do also here. So I put here the empirical density of states, and you know that is just the standard definition. I take the 1 over n. I have n eigenvalues, so 1 over n, and then I put the delta of w minus lambda chain. Right? Okay. So this I call rho n. So it's the sum of delta functions. So it's a random normalized random measure if you want. So and to make sure that you know it's a conserved quantity, I put here q. And then you know in the limit as n goes to infinity. I mean this is something which Alice then also proves, but you know sort of a general expectation is certainly correct in our case, is that you know this will go. To a random quantity, which actually is sort of like a smooth function, and well, okay, it has a density, and this will be, you know, this sort of law of large numbers. I mean, so let me just put law of large numbers there. So self-averaging law of large numbers, right? It's an almost sure limit. Okay. Okay, and so what you know just to re-emphasize, I mean, you know what once you have this law of large numbers, then you know the quantity which you can compute. I mean, this is what we did for the conventional hydrodynamics, but you know the same thing we need over here. So you know I want to take the density of the nth conserved quantity. Now this is now P and V as parameters of my generalized Gibbs ensemble, and that's of course simply the nth moment of this quantity, right? And so you see that you know once we know the density of states, I mean then you know we have already one key element which goes into the hydrodynamic description. So that will be a dw of w to the power n, and that's the rho q of w. Okay, so let me maybe I wanted to show this later, but you know, it's better if I start this at the beginning of the next lecture on Wednesday. But you know, just sort of you know the exam intuition. I mean, what this rho q actually looks like, right? I mean, so I will explain how one actually can write some formulas for this, but since time is almost up, I mean, let me just sort of end with a few pictures. So you might wonder, you know, so let's look at the similar equilibrium. That's sort of somehow the most physical case. Now there was actually an exact formula quite some time ago on this, and let's see. Okay, anyway, so let me just show you what they look like. Tell you the other things later. I mean, so yeah, you could look at let's see what I want to do. Just a moment. Yeah. Okay. So so let me put beta equal 1, and then let me think it of as a pressure. But you know, basically, you know, I want to look at nu. I mean, this is the average free volume. I mean, this is slightly more intuitive than the pressure at the moment. Okay, and so here is what you see. I mean, so this is W, and that's a rho Q. It's always the same same thing for the plots which I'm showing you. And if I make a nu very large, I mean, so nu is much larger than 1, then particles are very far apart. I mean, it's basically sort of like sort of dilute gas, no interaction whatsoever. And then, of course, I see the usually I know, so this is what I find. Now, I can be a little bit more ambitious and can ask myself, W, and then there's still the row Q. I can then ask myself, what happens if I put exactly nu equal to 0? This means that all the particles are sitting on top of each other, right? Because the free volume is 0. Okay. Then you see already a little bit more structure. I mean, sort of, look still the tail sort of look like discussion, but you get sort of like a small dip over here, and then it looks like this. Okay, but you see, I can also make the nu negative because I mean the particles simply reorder because I mean it's just the situation of very high pressure, and then if I put very high pressure onto this total chain, I mean then suddenly the particles don't want to order like in what I would naively think, I mean 1, 2, 3, but just reorder completely. And so if I make now nu much less than -1, then it becomes even more pronounced. I mean, so it will look like something like this. And then in the limit, it will go over to what people call the Arc-Klein distribution, which looks like this. Now, of course, this can happen only in the limit because whatever. I mean, even if I'm here over here, there's a general theorem that the support of this density of states will be always the infinite line. I mean, so you should think this of a limit where simply the tails sort of have gone to 0. And now you might ask, why do I emphasize this so much? Well, I mean, because you see already here the connection to random matrix theory. So here you have a 1 over square root singularity. And the connection to random matrix theory is that this is nothing else but, so this is the derivative of semicircle. So if I take the semicircular, I mean, which is this one, and if I take the derivative, then you find actually the distribution of the density of states of the total letters in the case when I put extremely strong pressure. Okay, so that's sorry for going over time, and I continue next time. I guess will be I want to explain you a little bit more of how one can actually compute the density of states in this case. All right.
Questions?
Too obvious.
These Lax matrices are always symmetric.
No. This is why I want to show that's a good question. Yeah. So okay. So okay. Okay. Let me put it. I mean, W static, which I hope to come to in towards the end of the lectures, they are actually unitary. Right? I mean, so it's not automatic because there are many cases where they are symmetric. Right? And then there's another terminology which I find useful. You see, this is something what people call the large Lax matrix, because it's an n by n matrix. And then there's also the smaller Lax matrix, which appears in when you do inverse scattering theory. Right? I mean, that's the one which you see immediately in the books, right? I mean, when people talk about, okay. Now, you see here we have a triangle matrix, and you can sort of, the eigenvalue problem for this matrix, you can also, because it's a triangle, you can formulate it as a problem on 2 by 2 matrices. And it, but the point is that the spectral parameter must come in a very special way. And if I take the general case of inverse scattering theory, apparently there is no big Lax matrix. And the Big-Lax matrix sort of has an advantage because you see, I mean, you know, it's really a matrix. And well, I mean, the other case is also a matrix, but the point is, you know, at the end, I mean, you take the trace of some complicated 2x2 matrix, and you look at, you know, sort of whatever, you know, what spectral parameters you have, and so I mean, the fact that you have this large n by n matrix is an important additional tool. You see, you can talk about eigenvectors of this thing, which when you look at inverse exactitude theory, you know, it's not clear whether you can talk of you know, n, you know, you know, whether there's a natural notion of eigenvectors actually. So yeah.
Any question? Okay, so if not, we can thank Herbert very much.